Welcome everyone to the 103rd online Spintronics seminar. Today we'll have the speaker, Professor Singh, received his PhD in physics from University of Central Florida in Professor Enrique Del Barco's group. He did postdoc in the groups of Professor Chris Hamill and Roland Kawakami at the Ohio State University. He joined the physics department at Carnegie Mellon University as a researcher professor in fall 2018, and currently he's an assistant professor in the physics department at CMU. His research group studies spin and magnetism related to emergent phenomena in novel quantum systems. And today he will bring us the field-free switching using tungsten telluride. Professor Singh, you have the floor.
Thank you, Shane, for the introduction, and thanks you and Carol for really inviting for presenting this work here. Today I'm going to talk about how we can use a layered material, 2D material, this particularly tungsten ditelluride, to achieve field-free deterministic spin-orbit Torque switching of a magnetic thin film with perpendicular magnetic anisotropy. So really, I don't think so we need any introduction here, but if you really think about field of spintronics, a lot of conceived applications, device applications, such as ultrafast magnetic memory devices, or neuromorphic computing, or oscillators emitting electromagnetic radiations at frequencies which are not otherwise possible. They all rely on a simple fact of manipulating or controlling the magnetic order in ferromagnetic or anti-ferromagnetic systems. And really, preferably, what we want to do is we want to control this magnetic order using electric field or electric current rather than external magnetic field. So over last more than a decade, it's been like a long time, we know how to do it, right? One way to do is through this phenomena of spin transfer torque, where what do you do is you take a spin polarized electron, and then you basically, when it interacts with a magnetic thin film, it transfers spin angular momentum to that system. And then if this and then due to this transfer of spin angular momentum, this magnetization vector in a, say, in a ferromagnet of a ferromagnet experience a torque, something we say the field spin transfer torque. And if this phenomena, if this torque is strong enough, right, you can either induce a complete reversal, or basically you can induce steady state precession. So essentially, it's in spin transfer torque, this interaction of electron spin and magnetization of thin film. So there's already very nice talk previously given by Professor Weyl on this platform about the fundamentals of spin transfer torque. So I encourage everyone to look there if you have any questions about it. So really, experimentally, how you do it? Well, you work with something called magnetic tunnel junctions, right? These devices where you have this free layer, magnetic field layer, and then this is what you want to manipulate, right? And it has basically a real life application, a commercialization even for MRAM technology, and then you can make these devices into really small footprint. But there are challenges of doing this magnetic manipulation using the spin polarized current or using spin transfer torque. For example, it may not be the most energy efficient way you can think of. And also these magnetic tunnel junctions, you have tunnel barrier in between oxide layer in the system, and then you're passing a large charge current through the system. And that leads to basically directly affect the device endurance, and then also joule heating that can lead to basically a lot of energy dissipation. Another way of basically inducing magnetization control or magnetization manipulation is through pure spin currents, right? And this is basically utilizing a phenomena known as spin Hall effect. Essentially, what happens in spin Hall effect is if you take a material, whether non-magnetic or magnetic, with sizable spin-orbit coupling, then you can get spin-dependent scattering of charge carriers in that material. And that leads to basically filtering of spin up and spin down charge carriers. This phenomena has been, observed experimentally long time ago, and in the field of spintronics and magnetism, we use it all the time. A lot of work is in this field using, platinum or tungsten or topological insulator using spin Hall effect in these systems. Now, if you go a bit more detail about this spin Hall effect phenomena, and then if I'm looking at a material thin film of, say, platinum or tungsten, then what you have is, some thickness. And then if I apply in plane electric field or charge current to the system, and then if I look at the cross section, right, just schematically, then theory of spin Hall effect tells you that this applied electric field or charge current, the spin current flowing, and this spin polarization, they are mutually orthogonal to each other, right? So these quantities are mutually orthogonal to each other. Now, if you take a thin film, really, to experimentalists, right, really either you have top surface available or bottom surface available, right? You can't really basically use this, if you have 2 nanometer, 3 nanometer film, you can't really use edge of the sample. And then if you apply charge current, then from spin Hall effect, we know that the spin polarization on the top and bottom surface is going to be in the plane of the film, okay? And now if I put a magnet near it, right, if I put a ferromagnetic layer to it, or say, and for that matter, anti-ferromagnetic layer, doesn't really matter, then there can be interaction of these spin currents with magnetization, and this can induce some kind of torque on this magnetization. And then most efficient torque is there are like different kind of torques acting in this scenario, but something very common we deal in this field is anti-damping spin orbit torque, or you can say spin Hall torque or spin orbit torque. And then what it does is basically, if this torque is strong enough, then you can induce precession, or you can even completely switch the magnetization direction of this ferromagnetic film. So essentially, it's basically more efficient. It's envisioned to be a more efficient way of doing magnetic manipulation as compared to spin transfer torque, because at the end of the day, what you have is basically, if you are trying to control the magnetization, you can couple it with spins. And then through this spin orbit coupling, you are coupling spin degree of freedom and orbital degree of freedom. And then through that, basically, you're coupling to your lattice. And then essentially, basically, what this allow you to do is it allow you to use basically angular momentum of the lattice for basically converting that angular momentum of the lattice for magnetic manipulation. And again, basically, there was a very nice talk given by Vivek earlier in this seminar series on this topic. So apart from basically, I will just briefly mention that apart from like this spin Hall effect, you can also have some effect, a phenomenon known as Rashba-Edelstein effect. Actually, this is more relevant if you are talking about material systems such as 3D topological insulators, or a 2-dimensional electron gas which exists at the surfaces or interfaces, right? Or some kind of Rashba interfaces. Here, what you have is, it's a purely interfacial phenomena most of the time. And then because of Rashba term in the Hamiltonian, you have spin momentum locking. And then what that means is that if you basically apply charge current into particular direction, if you move these Fermi contours, then you get basically automatic spin polarization, right? That's what happens in, for example, in surface states of 3D topological insulators. And again, basically, if you take this kind of system, you apply electric field, you generate in-plane oriented spin currents. And then again, if you put a ferromagnet near to it, then these spin currents can interact with that magnetization. It can put torque on that magnetization, and then you basically you can use that to basically induce some kind of control or manipulation. And this is not something new, right? It's been basically it's a very active field. And then I'm just showing one of the earlier experiments in this field where they used either whether it's claimed to be a spin Hall effect or Rashba-Edelstein effect in this bilayers of non-magnetic systems and ferromagnetic system, and then they use that to switch the magnetization of a nearby magnetic film through the spin orbit torque, right? And this has actually direct basically applications for, say, non-magnetic MRAM technology. On the other hand, basically, you can also induce steady state precession. For example, here, if you have polarized disk, and then I think bottom there it is, some kind of heavy metal, and then you can induce precession of this magnetization that can emit radiation, electromagnetic radiation in basically few gigahertz to tens of gigahertz range. And then that's basically application for an oscillator, right? If you want to build an oscillator. But still, basically, there are outstanding questions in this field. Particularly, the main thing is really like two things. How efficient is this spin to charge to spin conversion, right? And normally we like to quantify this efficiency in terms of a parameter known as spin Hall angle, which is nothing but a ratio of spin current to applied charge current, right? And then what you want to do is, in a material, optimally, you want to maximize spin Hall angle so that you can get efficient charge to spin conversion, or vice versa. And for that, we are continuously looking, people are looking for systems with large spin-off coupling, or system where you have, surface states, or, just like topological insulators or other exotic topological systems. Another thing which is important in this context is direction of the spin polarization. So if you look at spin Hall effect and Rashba-Edelstein effect in most of the system studies so far, until very recently, you will find that the spin currents are oriented in plane, right? And because they are oriented in plane, it has a huge implications for what kind of a spin orbit torque they can induce on the nearby magnetic film. For example, for sake of simplicity, you can take a spin source material on the bottom side. You can basically take a ferromagnetic material which has perpendicular magnetic anisotropy, and where magnetization is either stable in up or down, right, by stable configuration. And if I apply electric field in plane, it's going to generate spin polarization in plane, and then this basically, if this spin is this spin current is putting a torque on the magnetization, it will drag the magnetization towards in plane. And at this point, right, so if you basically, from this point, the magnetization can go either up or down. It doesn't have any preference, right? But then what people do is people basically apply external magnetic field to break the system symmetry, and that's so that you can achieve deterministic switching. And then, just to mention that why we need PMA materials, because, if you're talking about thermally stable, densely packed magnetic bits, your best bet is perhaps magnetic materials or magnetic thin films with perpendicular magnetic anisotropy. So that's the one way to basically, do deterministic switching of a PMA magnet with using, conventional spin source materials such as platinum or, topological insulator. But of course, people have found ways around it, basically, how to basically go around this problem, right? For example, I'm just basically, there are like very nice works out there. I'm just picking up just 4 of these works here. For example, you can basically use some kind of ferromagnetic and ferroelectric heterostructures to basically to achieve this field-free deterministic switching of a PMA magnet. Or basically, there's very nice work where they grew wedge kind of bilayers to break the system symmetry to achieve the same thing, which is field-free switching of a PMA magnet. And there's basically spin rotation experiments, and they're also using planar Hall current and so on. But then one can basically also wonder, right? Can we basically think of a material where basically you can think of a spin source material where you can generate spins which are not oriented in plane, but they have basically tilted out of plane? Well, of course, answer is yes, right? There was this very nice work coming out of Cornell Group back in 2016, where they looked at a material known as tungsten ditelluride. It's a 2D material, it's a layered material, it's a transition metal dichalcogenide, and they couple it with the a permalloy thin film, and then they looked at basically quantified the different type of spin torques acting on this permalloy thin film when they apply this RF current in different directions. And then what they basically shown, what they have shown in this work is that essentially, apart from basically in plane anti-damping torque, you also have some component of out of plane anti-damping torque when you apply charge this basically RF current in a particular direction, right? When you apply this the current which generates spin currents in WTe2 in a particular crystallographic direction. And it was argued on the basis of symmetry arguments, right? It was argued on symmetry consideration that actually this kind of system such as WTe2, you can generate out of plane spin currents, or you can say that you can induce out of plane anti-damping torque. So the idea here was simple, right? They argued that if you look at the crystal structure of WTe2, this is schematically I'm showing here. If this is a plane, I'm looking from the top. This is A crystallographic axis. This is B crystallographic axis, and then C axis coming out of plane. And then if there's a gradient, so this gradient basically of color which is shown to that basically there's a symmetry breaking, right? So there, if you look at basically BC plane, mirror symmetry of the system is preserved, but along AC plane it's broken, right? So in this kind of systems, right, again, basically these are symmetry arguments over here that basically how the current, if you reverse the current polarization of the spin charge, spin current should flip, right? And same for, this anti-damping torque, right? And say if you apply charge current along B axis, right? B axis where basically you have this mirror plane is along MA, right? If you apply current along B axis and then you perform mirror flexion, this operator RBC, then because this torque, right, it's a pseudo vector, right, and this reflection is the improper rotation, this should switch sign, but this current is not going to switch sign, right? So basically what this is kind of contradiction, because you are saying that you are saying that basically charge remains the same, but you can have polarization either pointing up or pointing down. That's contradiction, right? So that means you can't really have a non-zero out of plane anti-damping torque acting on or out of plane spin polarization when you apply current along the axis. On the other hand, when you apply charge current along A axis, right, this basically under same mirror reflection operator, you basically this this term torque term basically reverses signs, but at the same time you have basically a reversal of this charge current because you are now applying current this way, right? So here basically you can see that basically there's nothing prohibiting from symmetry consideration that you cannot have any out of plane spin polarization or out of plane anti-damping torque acting on this on nearby ferromagnet, right? So that was just schematic, but basically if you look at the crystal structure of this WTe2 or MoTe2, they exist in different basically in structural forms, either monoclinic or orthorhombic. And this orthorhombic phase for WTe2, which it is stable from low temperature, I think up to pretty high temperature, 300-400 Kelvin. On the other hand, MoTe2 also exists there, for example, from low temperature to I think maybe 270 or 80 Kelvin in orthorhombic phase. And then it has basically, particularly this orthorhombic phase, it has, rotation symmetry is broken. So this is the same case I was showing previously. So here basically you can see that if you apply current along a axis, then you should be able to generate out of plane spin currents. But that is just symmetric consideration, right? But you can basically do a more rigorous treatment. For example, here is you are basically, people have analyzed this one spin polarization matrix under mirror operation. So basically, if you apply a charge current to a crystal structure, then this generated spin polarization, this sigma, is product of this 3D magnetoelectric pseudotensor and this charge current. And then particularly, it was shown in this work that if you apply charge current along the low symmetry axis of WTe2, then you generate out of plane spin polarization besides this in plane spin polarization, right? So this was more rigorous treatment to dynamic symmetry arguments. So essentially, the deal here is that if you take WTe2 and then if you apply current along B axis, it's going to behave any other basically platinum system symmetry is basically same as a platinum or tungsten, and you're going to generate in plane oriented spin currents. On the other hand, if you apply charge current along A axis, then basically you can generate tilted spin polarization where basically you have some out of plane component. How much we don't know basically, but there will be some tilted spin polarization. And now basically, if you have tilted spin polarization, basically that breaks the symmetry of basically system by itself, in the sense that either basically depending on whether you're applying a positive current or negative current, this directional spin polarization will basically flip. So one will prefer a state up, basically magnetization up, and another will prefer magnetization down. So you can think of using this as spin source material to achieve field-free magnetic switching of a PMA thin film. Now that's about basically WTe2, right? That's what I'm going to talk about. That we use WTe2 basically to show that we can actually do that. And then I just want to briefly mention that WTe2 has very rich phase diagram. It's supposed to be a type 2 Weyl semimetal. It has quantum spin Hall state as well as superconducting state at very low temperatures. And there's some previous work done by basically in this paper where they shown that actually in Weyl semimetals you can have enormous electric field induced spin polarization. So you can think of that basically maybe a WTe2 is a kind of very nice material where you can induce out of plane spin polarization and then also get very efficient charge to spin conversion. And there are some very nice experimental works in this field where they use, for example, WTe2 to spin currents in WTe2 to switch the in-plane oriented magnetization of formulae at very record low spin currents, at record low charge current at room temperature. So really for us, the question was that, is this basically out of plane anti-damping torque or basically spin current is large? These phenomena large enough to switch the magnetization of a PMM magnet? That's what we were after, right? And for that, basically, we worked on basically all van der Waals platform for our SOT switching experiments, and we chose basically iron germanium telluride. I will use acronym FTT, which is a layer ferromagnet. It has strong perpendicular magnetic anisotropy. It has low saturation magnetization, high resistivity, basically good for these devices so that most of the current can flow through WTe2. It has atomically flat surfaces, which is essential for spin loss memory to suppress spin loss memory at the interfaces. And then also basically there's some aspect of some tunability. For example, you can tune the magnetism by changing the thickness, or basically perhaps by electric field. So what we did was basically we looked at bilayer structures of WTe2 and FGT, And of course, these materials, they degrade in ambient. For that, we use basically our glove boxes, which is connected to a UHV cluster system where we can grow, contacts and everything. So what we can do is we can exfoliate, flakes of hexagonal boron nitride. That's just protective layer everyone uses in 2D community. This is a thin layer of FGT, and this is WTe2. And then we use basically mechanical transfer techniques to get these films together to form heterostructures and then put it on pre-patterned devices. So at the end of the day, this is how our device looks like, capped with the HPN. You have WTe2 in contact with platinum contacts and FGT. Now, I think for these experiments, it's really important for us to know is which way is crystallographic A axis and which way is crystallographic B axis, because we really want to do control experiments. We want to basically apply charge current along A axis and apply charge current along B axis and look at basically response of the device. And for that, basically, we can use polarized Raman spectroscopy. This was first outlined in this very nice paper back in 2016. And these measurements were performed by our collaborator Rahul Roy at Air Force Research Lab in Dayton, Ohio. And using this one, we can actually exactly pinpoint what is the orientation of a crystallographic direction, and then so that we can put contacts in that direction, so that we can apply charge current in that particular direction. Also, one other thing, basically, if you think about van der Waal heterostructures, these are van der Waal, they are van der Waal gap, right? So you always wonder, whether basically spin can basically efficiently transfer across these van der Waal gaps, right? And then also, is this basically interface clean enough, right? Basically, if you're trying to achieve spin orbital switching, right? So you better have a clean interface. So most of our devices are characterized after we measure these devices using cross-sectional scanning, TEM, by our collaborator Jinu Hwang at Ohio State University. And this is one of the basic device, basically a cut of this device along B axis. And then if we basically, look at, interface of FGT and WTe2, it's pretty clean, it's atomically clean. You have basically very nice, nothing at the interface. So, that's really important for, these experiments. Now, basically, once we have these devices, right, what we can do is basically, before doing any switching experiment, we would like to look at basically any signature of this autoplane anti-damping torque or signature of autoplane spin currents, right? So we took a cue from basically this very nice paper back in 2018, where they looked at basically anomalous Hall loop shift, AHE loop shift measurements, where basically we measure the hysteresis loop of this bilayer heterostructure. Essentially, you're measuring FGT, and then looking at the anomalous Hall effect at different applied charge current to the system. And you can see that basically when we apply small current, positive or negative, the loops more or less overlap each other. But then basically when we apply, large enough charge current, we see a shift of this anomalous Hall loops to either positive or negative, depending on whether it's positive current or negative current. And this is a signature of basically this threshold kind of, basically if we plot the shift of these loops as a function of a current, positive or negative current, then we see basically very nice, threshold kind of behavior which splits up. And this is a signature of presence of, autoplane anti-damping torque acting on for a PM interior, right? On the other hand, basically, we expect that when we do apply current along B axis, right, because in these devices, basically, we have this cross junction, we can either apply current along A axis and then measure a Hall response along B, or we can apply current along B and measure a response along, A axis. So when we apply charge current along B axis, and not surprisingly, we see what we expect is that, even at basically higher charge current, the lower charge current, they'll overlap, but at even higher charge current, basically, they just shrink, but they don't move left or right, right? They are shrinking because you are basically joule heating, basically, it's affecting your hysteresis loop, right? the hysteresis field, right? Coercive field and everything. So this basically, really tells you that basically, this there's a presence of out-of-plane anti-dumping torque acting on basically magnetization of FGT when we apply charge current along a axis. So moving on, then what we want to do is we want to look at can we basically achieve field-free SOT switching of FGT when we apply current along a axis. And for that, basically, we just briefly, we basically probe magnetization of FGT using anomalous Hall distance. We basically apply, charge current, a charge current pulse, a large charge current pulse to switch the magnetization, and then we send a small delta pulse to measure the magnetization state. And then we basically increase the writing pulse and then keep on measuring and to see basically what's the magnetic state, whether it's basically moving from up and down. So this is basically one of the example of the measurements. We are sitting at 170 Kelvin. In our case, FGT is Curie temperature is around 220 Kelvin or 200 Kelvin. So we sit around 170 Kelvin so that we don't have to apply large charge current and of course for the GC. And then we see basically very nice basically square loop. Now basically when we apply charge current along a axis, right? Basically, what we do is we prepare state in either positive or negative, pointing negative or pointing up, direction by external magnetic field. We take that magnetic field off, and then basically we start applying a charge current. So basically, we apply charge current, measure the state, apply charge current, measure the state, apply charge current, and suddenly basically we see basically after some current, we see basically the magnetization switching from negative to positive. When basically we apply negative current, it basically stays negative. On the other hand, when initial state is in the positive, is pointing upwards, we apply positive current and then stays there. But when we apply negative current, it switches back, right? So really what it's showing you is that, the positive current prefers a positive state and negative current prefers a negative state, right? So, on the other hand, when we apply charge current along, B axis, right? And now this should be similar to what you expect for platinum or, tungsten or any other conventional, spin source material, because we're not applying any symmetry breaking field along the parallel or anti-parallel to the applied charge current. And then irrespective of basically whether state is prepared in positive or negative, we see that basically it's always demagnetized to near 0, 1. And then which makes sense that because now when we are applying current along B axis, there's not really any presence of out of plane spin currents which are breaking system symmetry. So they basically, once basically when you take the pulse out, it's equally probability. It has equal probability of going to this up or down, and then basically you get basically your magnetization of the thin film left randomly oriented, and then leads to basically demagnetization of FGT. So it's kind of a very we think that it's a very nice basically control experiment built into our samples where we can apply current along A axis and apply current along B axis, and then clearly see that we see basically deterministic switching when current is applied along A axis. Okay, so once we have that, then what we can do is, we can basically, once we know that how much at a particular temperature for a particular sample, what is the current is required to switch the magnetization, we can basically do this repeatable and consistent SOT switching measurements where we send a pulse larger than the threshold charge current required. For example, in case 9 milliamps corresponding to approximately 10⁻11 amp per meter square, and then by just switching the polarity of the pulse, we can basically go from down, up, and then this basically show you that you can basically very consistently we can switch the magnetic state of FGT. We looked at many samples. I think we looked at samples at different temperature, thicknesses of WTe2 ranging from 3 nanometer to 26 nanometer, thicknesses of FGT ranging from 4 nanometer to up to 16 nanometer or so, and then we consistently see 6-7 samples we see this behavior. which basically make these experiments pretty consistent and reproducible. We also basically, I'm not going to go into details about this one here, but there was also, numerical simulation done by our collaborator Ran Chang from University of California, Riverside, where basically we just took the case of monodomain FGT, but that just for intuitive purposes, because we know that mostly in our case, it's not a monodomain switching, and I will show some basic preliminary dynamics results in next couple of slides. But this basically numerical simulation did basically, at least it qualitatively, explained that basically, it's essential to have basically some kind of outer plane anti-damping torque to explain the switching that we see in our sample. Next, really, what we want to do was, we are looking at, what's the dynamics of this switching, and then basically if we can probe what's the mechanism of this switching. And for that, we are actually collaborating with Professor Katoch at Carnegie Mellon, where we can look at with the X-ray techniques such as beam formation, electron microscopy, coupled with XMCD techniques at advanced light source or other synchrotron facilities. And we want to basically measure these devices in apprentice devices under XMCD. And the really good thing about these devices with WTe2 is that basically we don't need any external magnetic field to basically initialize the magnetic state. Basically, we can apply negative current to basically put it down, and then basically we can switch back and forth by applying short current pulses and study basically kind of a time picture, time domain of this evolution. So for these devices, of course, there's some challenges associated with basically running XMCDP measurements. So we figured out a lot of technical details in these devices where basically we had WTe2 and FGT on top, and then our FGT is covered with graphene, single layer of graphene, just to protect this oxidation. And then, and not surprisingly, we only see domains, magnetic domains under beam XMCD when their graphene is covering FGT. And these are all basically our first measurements where we are measuring magnetic domains on operational SOT devices, mesoscopic SOT devices for this study. So if you look at basically active area, we basically ran some preliminary results where basically we apply charge current, and then again apply a pulse to along the axis, and then we see basically magnetic domains moving. So these are still very preliminary results, and this is work in progress, and hopefully we'll have something in the future. But the point here is basically we are looking at basically a time domain evolution of this switching using these devices with X-ray techniques. So very briefly, I just want to basically say that basically my group is actually also looking at basically beyond FGT. Really, basically, I think in case of particularly case of semiconducting and insulating ferromagnets, and particularly for the case of semiconducting ferromagnet, we are working with this chromium germanium telluride CGT acronym, where basically what we want to do is because CGT it has DC of around 80 Kelvin, but people have shown interesting things such as basically you can tune the saturation magnetization with the electric field and so on. So basically these are the additional functionalities that can offered by this material for spintronics applications. So we are basically working with basically tri-layer heterostructures where WTe2, CGT, platinum, where top layer WTe2 is basically used to write the magnetic state, and then bottom layer of platinum is used to actually read the state. And why? Because we are using platinum, because there's already a couple of nice work coming from different groups. They have shown that you can read the magnetic state of CGT with platinum. But I'll show briefly, we also successfully measured magnetic state of CGT with WTe2 as well. So this is basically where typical our devices looks like. So far, basically, this is work in progress, where basically basically we can make this complicated heterostructures, put them into devices, and then we can basically read the state of CGT, and then this work is in progress. Also, basically, we recently we have basically successfully used just WTe2 to measure the magnetic state of CGT, and where basically we just use bilayer of CGT and WTe2, and then basically just applying CGT is insulating, it's semiconducting, is at low temperature, so most of the current is going to WTe2. But through this phenomena of either proximity induced or spin Hall magnetoresistance, we are able to measure the magnetic state. And we can basically in near future we're looking at to basically run this spin over torque switching experiments. And lastly, I just want to say that basically we are also looking at a conventional ferromagnetic insulator system, such as TIG films, the tellurium iron oxide, where basically, for this, we are collaborating with a group of Pano Yang at Ohio State University. And really, on this front, the challenge is how to get basically a clean interface of 2D materials and 3D ferromagnetic insulators. We have actually, we have set up a nice capability where we can, transfer samples from one chamber to another chamber using UHV suitcase, and without breaking the vacuum, and bring it to our glove boxes to get a clean interface. And we are basically, making some good progress in this direction, where trying to get a nice interface for spin transparency across the 2D and 3D interfaces for SOT switching using this material. So to summarize, I will say that we have shown the first we have shown the experimental demonstration of field-free deterministic switching of a PMA magnet using autoplane spin currents in WTe2, and these TMDs are basically a very unique system for a spin source materials. We are still basically not sure about efficiency and everything, because still we have to apply pretty large currents to switch FGT at least at low temperature. And finally, I would like to acknowledge Daj student Ishan Kao, who did most of this work with help from Ryan Muzio, and undergrad student Jacob and Xian Zhang. And this work is done in close collaboration with the Professor Jyotikatoch at Carnegie Mellon. And lastly, our different collaborators for theory, experimental characterization, providing crystals, and so on. And finally, funding agencies for funding this work so that we can do it. And I will also use basically second to basically advertise that a postdoc position is available in my group. If you are interested, if you know somebody is looking for a postdoc, please ask me to contact me. Thank you.
Thank you very much for sharing this exciting research. We can thank the speaker using reactions buttons. And if you have any question at this moment, please raise hand in Zoom. And if you're watching this on Twitch, just type your questions in the chat box and I'll read it for you. Do we have any question here? Let me ask the first question.
Yes.
You show that you did the anomalous Hall effect basically by applying current along the A direction and B direction to measure the Hall voltage.
Yeah.
Do you notice any anomalous Hall resistance difference in the A direction and B direction?
So yeah, that's very interesting question actually. So we do see a small change in RX longitudinal resistance in along A axis and B axis, but we don't see much change in terms of RX by. And then honestly, I will say that we haven't looked that carefully about basically RXY, but we looked very carefully about RXX, a longitudinal resistance, and then we see a small change, small difference between along x-axis and along y-axis and b-axis.
I see. And just a technical question, between tungsten telluride and the FGT, which one has a higher resistance?
FGT has higher resistance, and then we also, what we do is we choose the thickness of FGT and WTe2 such a way that in most of our devices, the more than 90% current is flowing through WTe2. So,
oh, I see.
Yeah.
I see. Yeah. Thank you. Do we have any other question? Oh, Evgeny, please go ahead.
Thank you for a very interesting presentation. I have a question regarding switching of your FGT. So
yes.
What you're saying is that when you're passing current along A and B, in one case you have deterministic switching of the FGT, and in another case you have basically Joule heating and demagnetizing of your film. But if you go to this slide, I think it's the next slide, maybe a couple of slides. Yeah, this one. If you compare now the current density which you need for switching to the current density which you need to demagnetizing, because it's nearly the same current density. So I'm just wondering if the Joule heating is necessary to observe switching. Is that kind of assisting process to observe switching?
Absolutely. Excellent question. Yes, excellent point. Yes, you're right. It's thermally assisted. We definitely think that it's thermally assisted switching. But I can tell you that, basically when we are giving a picture, very a qualitative picture along when basically, you are heating along B axis, of course, we are also heating along A axis. And then we have done basically temperature profile study of this one. And then we know that, temperature gets very close to, TC when the pulse is on, but it's always remains below because we can measure anomalous Hall loop at the switching current. For example, if switching, in this case, switching is happening at 8-9, completely around 8-9 milliamps, we can, if we measure the anomalous Hall loop at 9 milliamps, we do see a basically clear loop, but smaller loop. But definitely you're right, it's a thermally assisted switching, we think.
All right, thank you.
Great. Do we have any other questions, comments? Very quickly for the X-ray beam experiment that you did, I missed something. So essentially, even if you apply current along A, you don't get a full switching. Is that correct?
Yes, you're right. So these were, the data I'm showing here is basically very preliminary, because I think one of the issue we are dealing with, these devices is that, the device is under influence of very large vertical electric fields for beam, and it destroys the device. And and then here basically you can say that basically, even when because in this setup we didn't have really out of plane magnetic field to initialize the state, right? But our idea was that, okay, perhaps we can basically, we should be able to actually apply current along A axis and then either switch it to basically bottom or up, right? But definitely in these experiments that I'm showing, we were not able to do it because we were not able to pass large enough current. But I think the point was that I'm just showing from basically from this point of view that basically, we definitely, if I basically look at this image and this image, two successive pulses, we definitely see change in the contrast of domains at a particular point that they basically it's getting more white, or we haven't done basically quantitative analysis on these samples, but we think basically we have actually beam time starting this weekend, so hopefully we'll have something more.
I see. Thank you. Hanuman, please go ahead.
Hi, Dr. Simranjeet. Really great talk. So I have a question also on this beam measurement. So in this beam measurement, are you taking on this in plane sample or out of plane sample?
This is out of plane.
Or also, I'm just asking, this is done in ALS, LBNL, or
Yes, yeah. So
somewhere
it's
else?
done. Yeah, it's done at PIM3 at these particular experiments. This
ALS, LBNL, right?
Yeah,
Also,
PIM3.
but
Yeah.
normally they don't have access for the out of plane. I used to use this, and they always get for the only in plane measurement. And
yes,
I'm wondering, means.
Yeah, you're right. We didn't apply any. That's what I was saying, that we couldn't apply any out of plane magnetic field, because to begin with, basically, we cool down, we have these domains, but we couldn't basically saturate into out of plane or pointing up or down, because we cannot apply out of plane magnetic field. But
so basically, your first initially your magnet is out of plane, right?
Well, you will think, but not really. For example, when we just cool down, we have domains. We don't have it pointing down or up, because we didn't have access to out of plane magnetic field.
Yeah. Okay.
Does that make sense?
Yeah, slightly, because I used to use this. I heard all that, and most of these images look like when you have in plane or in the one direction, you always get this black and white is regarding this. So both time in this PM11.3, we are getting this image for only in plane. There is no signal for the out of plane. Always we get this gray contrast either on top or bottom. So I'm just wondering, this is really you have out of plane device or only just in plane sample?
This is basically FGT, which has perpendicular magnetic anisotropy, cooled down below TC without any magnetic field. And then we were trying to basically use current pulses to basically move into one direction, which we haven't done successfully yet. The only thing we see is basically, if you look at this surface, this one here, compare this picture here, this picture here, basically, we are definitely moving some domains. That's the only thing we have so far.
Okay, yeah, thank you. Yeah.
Thank you. I think in the chat, Dr. Carlos Rojas said, asked the related question, is wondering if the anomalous Hall effect amplitude you get in the RXY versus current is the same as RXY versus HZ. Probably from there you can tell whether it's a fully switching of your device.
RXY versus current and RX versus HZ. Yes, I think it's fully switched. I think if I understand this question,
right.
I think question is this one here, right? Basically, whether this one is, for example, 300 and minus 300 million, right? Millions. And then here, basically, this is basically 300 and minus 300. So we think it's fully switched. It's like basically, and this is.
Yes. Yes, I see. Yeah. Thank you. And Kirill, please go ahead.
Yes, thank you. Very interesting talk. So I wanted to ask if you have some sort of statistics among a bunch of different samples, or how many samples did you get? Like, I'm wondering, in particular, since you're putting flakes on top of each other, so you can have potentially devices with different angles between the crystallographic axes of the TMD and FGT, right? So you're assuming that's what's important is the crystallographic orientation of the TMD. But is the crystallographic orientation of FGT irrelevant? Have you looked into that? Do you know something about it?
Yeah, that's a good question and interesting question. We live in the age of Moore superlattices, right? So definitely we haven't, the only thing we paid attention, basically, I think so far, basically, we might basically total 10 devices or something like that. And we were always, paying attention to that, basically, where is A axis relative to our contacts, pre-written contacts. So we never paid attention towards FGT, And that's also because some technical issue, because it's very hard to get the flakes of FGT. And then basically, it's very hard to manipulate them and stuff like that. So most of the time, we never paid attention to crystallographic orientation of FGT in our samples so far.
But do you have statistics over different devices? Like, do you always get the same angular dependence, for example?
For WTe2 along A-axis and B-axis?
Yeah, like I imagine you would make several different devices, right?
Yes.
And you observe the magnitude of the effect. So is it always similar?
Yes. So
different devices, or is there a range?
No, it's always different. So basically, I can say that basically my student is very good at basically. Okay, so let me basically, maybe that will help you. So always when we exfoliate WTe2, we can tell which one is A-axis. And that is always basically the flakes will cleave. Thermodynamically, they cleave along A-axis. And even if you look at the crystals of WTe2, they are needles. So when we cleave them, I can basically look at this one and say that basically whenever I see two parallel faces, two parallel sides, that is A-axis. And then every time, 100% of the time, when we do polarized Raman and STEM, we always find that this is the A-axis. And then what we do is basically when we are making these samples, we basically align this A-axis with basically these electrodes. So all the time, basically within, of course, I think 1 degree or something, we are always precise with respect to crystallographic orientation of WTe2 in our sample. And we always see switching along A and no switching along B.
And what about the switching current, for example? Is it similar to different devices?
Yes, it's. I think it's very high in all of the order of 10 to the power 11 amp per meter square, and yes, so it's in the same order. We don't see basically a lot of changes. But then again, basically, we are doing some kind of approximation, because if you look at our, samples, we have FGT, which is conducting, is higher resistivity, but still conducting. And we don't have basically really, I wish we had basically, in the device, we can measure conductivity of FGT alone and WTe2 alone. But here, basically, we do some kind of, based on basically flakes that are measured separately, which have similar thickness. But we also know that basically, even if you have similar thickness, there's always variation in 2D samples. Even if you take a graphene, you make one day, another day, it's always a different resistivity. You can get different resistivity because they are very sensitive to environment and everything. So we don't have any, I'll say that honestly, we don't have any strong proof or basically tangible data which can tell us that we can compare one sample to another sample in terms of how much current variation we are getting.
Mm-hmm. And is it always a single layer flake or of FGT, or can you make different thicknesses?
Oh, it's never a single layer. Basically, the thicknesses in devices, the thinnest we have gone is 4 nanometer, and then a maximum we have gone is 16 nanometer, 16 nanometer. For the case of WTe2, we have gone from 2 nanometer, I think it was 3 nanometer to 26 nanometer. These are the devices where we have measured basically field-free switching.
And how does the switching current depend on the thickness of FGT?
FGT, I wish. Let me see. I may have data.
Because you expect a certain kind of scaling if the
yeah, a certain kind of scaling if we have same thickness of WTe2. So in each sample we have different thicknesses of a WTe2 and different thicknesses of FGT. That's the problem for us.
Mm-hmm.
Yeah, so basically we can't really compare basically one sample with another sample exactly, right? But we just say that okay, one is 20 nanometer And so what we tend to do is, if we get 4 nanometer of FGT, we try to get basically a 20 nanometer of WTe2, so that most of the current flows to WTe2. If we get basically 10 nanometer of FGT, then basically what we give, we go a little bit higher, 30 nanometer. So we try to basically make samples such a way that most of the current is flowing through WTe2, because for us it's very hard to basically get
yeah, but even with that, because it's an interfacial effect, right? So your switching current is expected to scale, I suppose, proportional to the thickness or something.
Okay, so we can look at here actually, for example, device 1. Let me see. Device 1 is basically, I can give you thicknesses, maybe that will help. Yeah, maybe I should have shown this in the beginning when you asked this question. That would be less confusing. Okay, device 1. So on the right here, basically WTe2 was 26, and then FGT was 4. Device 2 was, I think, 24 WTe2 and 7.7 FGT. And if we compare at 170, say this one is switching happening at 5 or something, and here basically a little bit higher. So it is happening at a little bit higher current than
So device 2 is thicker?
Device 2 is thicker FGT. Yeah, 3 nanometer thicker FGT. Okay. And almost same thickness of WTe2. This one is 25.8 nanometer, and this one is 24.4 nanometer.
Mm-hmm. Yeah. Yeah, it would be nice to know that it scales with the thickness of FGT, like you expect the spin orbit torque to scale.
I see. So you're thinking if we keep the same thickness of WTe2 and then change the thickness of FGT?
Well, the thickness of the TMD probably doesn't matter in terms of the generation of spin current, but
the anisotropy could be different, and the pinning field can be different. So it's comparing the switching current. It may not be. You may not expect the exact one with
yes, that too. Yeah. Mm-hmm.
Yeah.
So if the torque could be measured directly, that would be a better measurement, I suppose. Yeah. Okay. Thank you.
Professor Fei Xue, please go ahead.
Thank you for the next talk. Related to Kirill's question, actually, I'm trying to see, in your device and sample variation, do you see any polarity dependence? What I mean is, in these TMDs, each layer has different in-plane symmetry polarity symmetry breaking, right? And in your making your flakes on top of each other, you might have opposite polarity or out of plane torque generation, depending on the electric field current direction. So I mean, for example, it looks like in your all 3 devices, you apply same direction electric field. They, when your change your magnetization to the same direction. You didn't see any variation?
No, we never saw any variation. Yeah.
That's a little bit different from the Cornell's experiment, right? They measure the, they use this as spin Hall FMR. Yeah. They see the different sign of the torque depend in their device variation because they cannot control that.
Yeah, so I think they basically can go across the step, right? 1 layer and 2 layers, and then they can do it, right? And in our case, basically,
but this is not just a layer, it's just interfacial, right? You don't know interfacial in your device which interface you get, right? You just stack them.
Yes, but so you mean basically, sorry, I'm not getting your point. So you're saying that which layer of WTe2 is?
Yes, which in the interfacial between FGT and WTe2, you might get different, impedance symmetry breaking direction, polarity in that sense.
Yeah, but I think just to be sure, those STFMR experiments they're particularly sensitive to that one, because you're doing basically literally basically going in all directions, and then basically you can pinpoint from the angular dependence what's going on. In our case, basically we literally basically what we are doing is initial state and final state. We don't know anything else. So that
but if let's imagine I'm saying your P can M cross P. This P can be plus Z or minus Z, depending on your device interfacial configuration. Do you see any evidence showing that?
As I recall from basically over approximately 7-8 devices, we always see the same behavior. One thing we see is basically one thing weird we see is basically when we apply a current along B axis, in terms of it should behave as platinum, we should have basically counterclockwise or clockwise polarity. That polarity is we see all over the place. Basically, yeah, sometimes it's basically makes sense, sometimes it just switches sign, and that basically we could never understood, and yeah. But along the A side, basically it's always the same.
Okay, thank you.
Great. Do we have any other question? Let me just quickly check Twitch. There's no question on Twitch. Okay, if there's no other question, I want to thank the speaker again. And I want to thank everyone for attending. We may have another short session for further discussion afterwards. But at this moment, I would like to just pause the recording and turn off the live streaming.